Perfect. So we are recording now. We can start with questions. Anybody wants to volunteer and start? I saw Talal. Yeah, go ahead, Talal.
Just a quick question. Can you go over question 2 in the practice exam?
Okay,
Like
sounds
just
good.
in general.
Which is the pressure drop, right? The P in the,
Yeah.
yeah, okay. So practice exam, question 2. So basically, the problem is asking that what happens if we are pushing some water up a vertical pipe. The outlet pressure is P out is 0. P in is something we are being asked to graph. And the velocity is given as U. U average is U. And the flow is under laminar condition, and which of the following plots describe the relationship between P and U. So first, this is not a horizontal straight pipe, so we should use Bernoulli's equation. Remember, whenever you see a horizontal straight horizontal pipe, you can use the pressure drop is equal to friction factor relationship. But whenever you have a vertical or an inclined pipe, you want to start with modified Bernoulli's. P in by gamma, V in square by 2G plus Z in is equal to P out plus V out square by 2G plus Z out plus loss, which is U square by 2G, U pipe basically, into FL by D. So now we know P out is 0. We also know V in is equal to V out because the pipe is straight. So A1 V1 AV in is equal to AV out from the and so we can cancel that out, and Z in minus Z out is L. So Z out minus Z in is L. So P in by gamma equal to Z out minus Z in plus U square by 2G into FL by D. Right? And this is the length of the pipe. So the first point is that even if the velocity is 0, I do need some pressure to keep the water, which makes sense. Like if so that the water doesn't stop falling down, I need some pressure to continue for the water to at least stay stationary. So at U is equal to 0, my pressure cannot be 0 because I have the Z out minus Z in. And then F is 64 by R in Reynolds number, which is why you get a linear profile. So that's why you have P in versus U as something like some non-zero intercept and a linear profile. So that's the idea. So that's why the answer is B. Make sense, Talal?
Can you say why? Can you tell me why the graph would not go through the origin again?
Yeah, because if U is 0, so if I put U as 0, so substitute U is equal to 0, then my P in by gamma is equal to Z out minus Z in, right? And this is not, this is vertical. So this can never be 0.
Okay. Yeah, I got it now. Thank you.
Yeah, for sure. All right, so a lot of students have joined. Yeah, we are going just one by one, and I'll take all the questions. So don't worry. I'll make sure all the questions are answered. So I forgot who came first, but perhaps yeah, I see Owen has raised hand. Anybody else has questions so that I can go in order? So Owen has raised hand. Anybody else? Okay, so Owen and then Kevin and then Jackson and Sam. Okay, so Owen and then Kevin, Jackson, Sam, and then Hassan. Okay, so let's go Owen first. You can go ahead.
So I have a question about number 3 on the practice exam.
Mhm.
In your solution, you say delta P is like approximately equal to U to the 7/4.
Yeah.
And I'm just wondering, like, when you do that calculation, like what leads you, because I know like all the units like don't cancel.
Yeah,
So I'm just
absolutely.
like confused on when you should know like, oh, like all this doesn't like have enough of an effect on
Yeah,
the
absolutely.
equation, so we can just say that this is approximately equal to that.
Yeah, so I should note first, it's not an approximate sign, it's more of a proportionality constant. But let me try to explain this more clearly, okay? So first, I just want to again emphasize for others also who have just joined on the call that it's a horizontal pipe. So in a horizontal pipe, you can use this relationship that rho U square by 2 is into FL by D. Or alternatively, you can say friction factor is delta P by rho U square by 2 into L by D. And so what Owen was asking was, how do I know what to keep constant and not to keep constant? Remember, my pipe is the same. So first thing is, because this is a horizontal smooth pipe, I've been given that friction factor is 0.316 into Reynolds number to the power of 1/4. So delta P is equal to rho U square by 2 into 0.316 into rho U D by mu into 1 to the 1/4 into L by D. Now, the main point over here, it is basically that note that I'm keeping the same fluid. I'm not changing the fluid, so rho cannot change. I cannot change rho. I am not changing the pipe length or diameter. So D and length and diameter are the same. Viscosity is the same. And then obviously the rest of the things are just coefficients. So that's why I said pressure drop. And because there is a U square and a U to the 1/4, that is proportional to U to the 7/4. And the rest of the variables, they are there, but they're all constants. They're not changing from one experiment to the other experiment. And that's why we can ignore them.
Okay, perfect. Thank you so much.
Yeah. So let's go with Kevin, then Jackson and Sam, and then yeah, we'll go. Kevin, go ahead.
So in class we derived the non-dimensionalized Navier-Stokes equation, and it was done one time in a homework question. I didn't see it mentioned, at least from a quick glance on the practice, that it was on there. Is that something we should be studying heavily, you think, for the final?
Yeah, non-dimensionalized Navier-Stokes equation is not a priority. So I would say what you should be able to do is basically for any equation, not necessarily not, for any equation, you should know the basic process. So what do I mean by that? Know the basic process. So let me try to explain to you. So if I have some sort of F is equal to M du by dt, and I tell you that T star is T by tau, U is equal to U, U by U star is U by U naught, and stuff like that. You should know how to be able to substitute it, but I wouldn't worry about memorizing it or working in too much detail. It'll be something simple, but not anything that will be in detail. But you should be just aware of how to substitute and get it out, but don't worry about remembering the full Navier-Stokes equation.
Okay, thank you. I appreciate that.
Yeah. I think it's Jackson next. Yeah, Jackson, please go ahead.
Okay, so I'm a little confused on when we're doing the modified Bernoulli's equation. We have the major and minor losses. I don't know specifically for the major and minor losses what velocity to use specifically.
What velocity to use?
Yes.
Okay, so let's go here. All right, so remember that, so this is the major loss. Okay, so now let's discuss each component. So the question is which velocity to use for each loss. So the most important point to remember is we have to use for the major loss the velocity of that particular pipe. So let's take an example. If I have an example where I have a pipe like this and a pipe like this, then I'll have two, let's say this is U1, this is U2, okay? U1 slash U2. So my HL in the major loss, and this is L1, L2, D1, D2. Then my pipe loss will have to, the major loss will have to be U1 square by 2G into FL1 by D1, rather F1L1 by D1, depending on the Reynolds number of the pipe. The friction factor might also change. U2 square by 2G into F2L2 by D2. So essentially, this is whatever is the velocity within the same pipe. That is what we have to use when we are summing up the major losses. For the minor loss, however, so KL UL square by 2G, this is something you shouldn't worry about. This will be provided. So we'll tell you, use the velocity in the larger pipe or use the velocity in the smaller pipe. that will be explicitly mentioned, and so you don't have to worry about it. And if it turns out that that we say ignore minor losses, then you can just obviously ignore this term. But it's very important to remember that all of these terms have to be within one pipe. And because in this course, we are not changing the diameter of the pipe within a pipe, like this pipe only has diameter D1, it's not changing with it along the length of the pipe, the velocity will not change. So that's why you can use one velocity within one pipe. So make sure in the major losses, the velocity is the velocity within the pipe. Okay. Does that make sense, Jackson?
Yes, that makes sense. Thank you.
All right. I think after Jackson, it's Sam. Sam, please go ahead.
Could you please explain 5B?
5B in the practice
Yes.
exam, right?
Yes.
Yes. So I can explain it. I would highly recommend to not worry about it for the exam tomorrow.
Oh, okay, got it.
Because it was an advanced question, and you will not be asked anything like this tomorrow. Like I mentioned, exam would be representative to the final exam. The practice exam is hard. You would see that in the final exam as well. But this problem, like something like this, won't be tested. So first, I would not worry about that. But let's still discuss. I just want to mention it in case somebody's curious here. So the main idea here is, and I forgot how. Let me just check the solution. What's the pi's given in the solution? So the pi in the solution is t by rho omega square r to the 5. And the main idea behind this particular problem was that the t is proportional to force, which is proportional to stress, and that stress is proportional to 1 by h. So that was the key idea. And so that we need to have inverse relationship with the height. And basically, if I keep making smaller and smaller and smaller height, the shear stress is going to go higher and higher and higher, and that will change force and that will change the torque. So that's why we want 1 by h dependence. And to get 1 by h dependence, essentially we will multiply this by rho omega square r5 into r by h. And so this is why we'll define some pi prime. And so this will become rho omega square r4 into 1 by h. So that was the idea. And if you look at the practice solution, I had a different dimensionless group there. And still I basically forced it to be a relationship with 1 by h. But again, I wouldn't worry about it for tomorrow. I would say this was a very difficult question. And so something like this will not be tested tomorrow. But hopefully sort of the rationale makes sense what I did here, but I wouldn't worry about it for tomorrow. Okay. Does it make sense, Sam?
Yes, thank you.
Okay. All right. So let me go to Hassan then, and then Trio, and then we can go back to Talal. Okay, Hassan, please go ahead.
Yeah, for 7B, I'm just not sure how you derive the equation.
Okay, yeah, sure. So 7B, how did we derive the equation? So was it the first equation or was it the integration?
Just like the question itself, like where you
Okay.
got
Yeah,
the
sounds good. Yeah, okay. No, I hear you. All right. So the question is what is essentially even going on here? So in the B part, just to make sure, yeah, the parachute has been opened. So there's a person where like a parachute has been opened at the back, and you're moving with some velocity u naught. But at this point, if you look at the problem, it says that you open the parachute, but you turn off the turbo mode. And so essentially you're not applying any force, because turbo mode mean you're propelling with the force, but now we don't have any propulsion. But because we have some velocity, we'll still feel some drag, right? So we'll feel some drag. And so the point is mass times acceleration, m times du by dt is equal to drag, because we are still going in the right direction, but the drag is opposing me. So I'll start to slowly decelerate. So that's why I have a negative FD, because it's going to oppose my rightward motion, let's say. So because of that, now we'll say m du by dt. Drag force is given by minus rho u square by 2 into CD into area. And then I can say here du by minus du by u square is equal to CdA CdA by 2m rho dt. And I will go from some time t equal to 0 to time t. T equal to 0 means when we stopped, opened the parachute and stopped the turbo, opened the parachute. Then I will have minus d by u square from u naught to u. That's the velocity again when we open the parachute. And that's how I got the 1 by u naught minus 1 by u. Actually 1 by u minus 1 by u naught is equal to rho CdA t by 2m. And so that's how it was derived. I'm happy to discuss in more detail, Hassan, if this is not clear.
No, I think that answers it.
Okay, perfect. All right, so I think I remember Nicole also had a question, but I don't see the hand up now, so probably it was answered. All right, so now next go to Trio, and then we'll discuss. Trio, go ahead.
I have the same question as this, but how do you derive the time 1/2 equation from this?
From this, yeah, okay, perfect. So the question is, how do we derive t1/2? So at t1/2, we want u is equal to u naught by 2, and at that will happen t is equal to t1/2. And so I'll substitute this. So substitute, so I'll get 2 by u naught minus 1 by u naught is equal to rho CD A t1/2 by 2m. So t1/2 becomes 2m by rho CdA u naught. That's what you get, I think. Yeah, that's what you make sense, True?
Yeah, thank you.
Okay, perfect. I see another chat. Why do we not add the area of both the person and the parachute? You can absolutely do that, Jackson, but because the problem specified the area, if you look at, so the question Jackson is asking is, why did not we add the area of the person and then the area of the parachute? You could do that, but if you look at the schematic in part B, we did not include the person of the area, but if you add it, it will be 0.5. And I mean, you can always add it, but it will be so small that it would basically not matter that much, but you don't have to add. I would just say, whatever the schematic is given, just use that as a reference because you don't want to overcomplicate and overthink it. In reality, it should be both of them, but that's the simplest way to think about it is the parachute kind of encapsulates the person as well effectively, basically. Yeah. All right. Other questions? Dylan, yeah, go ahead. And then I'll come back to you, Talal and Jackson. Okay. Dylan, go ahead.
All right, I just had a quick ones from redoing the homework problems. So homework 9, we used centerline velocity for Reynolds number, and I was wondering, do we always use the centerline velocity? And also, is the centerline velocity always just half of like the velocity in the rest of the pipe?
So good question. So actually for Reynolds number, we always use the average velocity. Okay, so for Reynolds number, you always use the U average. We don't explicitly state that, but remember you always use the U average. And the way to remember, I would say U center is 2 times U average. Average for a pipe in laminar conditions. Laminar conditions. Okay, so if you're given a center line velocity, you can calculate the average velocity in the laminar conditions. Okay, in the turbulent conditions, I wouldn't worry about remembering that formula. So the reason I'm specifying this is, so if a problem gives you a very high Reynolds number, then don't use this essentially. Okay, there will be a separate relationship that will be given to you. You don't have to memorize it, but this is only true for a circular pipe and laminar conditions. This is not always true.
Okay.
Yeah, perfect. All right. Just I have another hand up from Ari, and then I'll go back to the students who already asked a question. Ari, go ahead. Yeah.
I have a question about 7B as well.
Okay. Yeah, go ahead.
Why do I guess my question is differences between A and B. And why do we have on B, we have M times dv dt, and we don't have that on question A? The
Yeah,
only
very good
difference that I
question.
see is that in B it's decelerating. Maybe that's why.
Correct. Yeah. So remember, the first question is asking you the maximum velocity. So let's imagine there was jetpack. Now you started the turbo. So the question is, why do we not have the acceleration in the A part? Very good question. We don't have an acceleration in the A part because we are looking at the case when the maximum velocity. So the maximum velocity will come when du by dt is zero. You want to get a maxima. And initially you will, let's say, start with zero, you accelerate, the drag keeps on increasing, increasing, increasing. And then at one point, the drag and the propulsion force have balanced each other out. So that's the maximum velocity. In this case, we can also call it the terminal velocity if you want. But in the sense, maximum velocity essentially represents the case when the acceleration is basically zero, because I cannot accelerate anymore, right? So that's why it's mdu by dt is not there in part A. But in part B, I am actually decelerating. My velocity initially was 20 meters per second, and I am changing with time. I'm decreasing my velocity with time. So mdu by dt is basically negative, and that's why I'm decelerating, and that's why it's included in the problem. Does it make sense?
Yeah, that makes sense. Thank you.
Perfect. All right, any other questions before I go back to Jackson, Talal, and Owen? Anyone? Please feel free to raise your hands. All right, I'm assuming nobody else has a question, but you can always jump in if you want. Just raise your hands and we'll get to you. So perhaps we can go back to Owen, then Talal, and then Jackson. Owen, go ahead.
More of just a general question. Is there anything that wasn't explicitly tested on in the practice exam that you feel would be valuable to know, or do you think the practice exam is like would give you a pretty good understanding of your knowledge?
Yeah, no, there would be no additional concept, just obviously the questions will be different, but no additional particular concept that you have to worry about. Like I think I've mentioned before, make sure you are comfortable with pipe flows using different friction factors, and the scalings of that. In the terminal velocity case, make sure you are comfortable with doing force balances, either horizontally or vertically. And then the dimensionless groups is pretty simple with Buckingham Pi theorem. So yeah, I wouldn't worry. There's no additional concept. You just have to be, make sure you're reading the questions well, managing your time well. As this exam, it is going to be a difficult exam, but I wouldn't worry about any new concepts per se.
Could you do a quick example of horizontal versus vertical?
Yeah, absolutely.
Pipe, like just like what the difference, what is changing, and like how you should treat them.
Yeah, absolutely. So horizontal versus vertical. Okay. So let's do this. Okay. So how the question is, we have been given, let's imagine, and I'll make this one up. So I've been given some pressure drop here, and I've been asked, I'll just assume a rough pipe for simplicity. Rough pipe, which means F is constant. Okay, and then I have this case. The question is, what's delta P here? Delta PH and delta PV. Okay, so I've been asked, what should be the delta PV here to keep same flow rate? To keep same flow rate. Okay. So first, I hope it makes sense. The first question, it should make sense that I should need more pressure drop in the vertical pipe, right? Because I'm pushing something up. And then length L and diameter D. Okay, so let's do this here. So delta PH, I know is rho U square by 2 into FL by D, all right? And so I can now say Q by pi D square by 4 whole square, okay? So I get delta PH is equal to rho Q square, pi D square, so 4 square, 16 by pi square, by D to the 5 into F times L. Okay, so I'm just rearranging this by substituting the value from flow rate to the diameter. And why have I done that? Because I've been asked to keep the same flow rate. So that's why I'm going away from the velocity to the same flow rate. And then delta P vertical would be P in by rho V, P in by gamma rho v in square by 2g. I have to use this because now I am in the same what should I say? I'm in the modified Bernoulli's case because I'm not no longer in the horizontal pipe. So then I have rho v in square plus z in is equal to p out by gamma plus v out square by 2g plus z out plus u square by 2g into fl by d. Now again, I get delta p v by gamma here. This cancels out because p in minus p out is delta pv is equal to z out minus z in, which is L plus u square by 2g into fl by d, fl by d, and this is again q by pi d square by 4. And so this tells me, if you think about this, this number is identical to this number here, but with by gamma, so I'll get delta ph pb by gamma is equal to L plus delta ph by gamma. It's a little bit, I've rushed it a little bit, but hopefully this kind of makes sense that I'm equating, because my q is the same here. I'm just equating the formula from with the delta pH and trying to get to the same point. So in this case, I need more pressure because I'm also fighting against gravity. Now I could technically make this D2 and L2, in which case you have to keep a D2, L2, L2 here, and then you will have to substitute the same flow rate formula. It will become a bit more messy. I wouldn't worry about like this. It won't be this messy, but hopefully like the idea makes sense between, horizontal and vertical pipes.
On the horizontal, where there's the q squared over, what is that? Q squared over
D to the 5,
D?
because
D
D to
to
the
the
5, because D square, the whole square become D to the 4, and then there is also a diameter here. That's why it's D to the 5.
Oh, perfect. Thank you.
Yeah. All right. So I think all the students who have raised their hands currently are the students who have asked the question before. So I'll go in the order. So let's go with Talal and then Jackson. Talal, go ahead, please.
Yeah, I just have two questions now, actually. For question 4, when we check the Reynolds number to know if the conditions apply or no, how can I know which density or viscosity should I use?
Yes.
Like the water or the air
Yeah.
or the object?
Yes. So for Reynolds number, always make sure, always use the density and viscosity of the fluid in which the object is moving. Okay, the object is moving. So let's discuss this. Okay, so if I have a rho solid, rho mu, and diameter, and this is settling with the velocity u, then Reynolds number will be rho u d by mu. And if I have a bubble, rho b, rho mu, rising up with the velocity u and diameter d, even in that case, it will be rho u d by mu. So in both of the cases, the Reynolds number is the one which is outside. It is never take the Reynolds number of by using the viscosity and density of the fluid that is moving. It's always the surrounding media, because that's what sort of, is critical. So make sure to use it of the fluid in which the flow is happening. Make sense?
Yeah, makes sense. Can you go over question 6a as well? Like the derivation of the Bernoulli?
Oh, yes, 6a. Yeah, of course.
Yeah. So it's
6A.
kind of not clear in the solution.
Yeah, of course. So P6A, so it's this part here, and then we have this here. Okay, so we have this is theta2, this is theta1, theta2, theta1, and then we have theta3. Okay, so the question basically states, if I remember correctly, that the pressure inlet and the outlet is equal. The velocity is going in this direction, gravity is in this direction. I mean, it's up to us. I can say this is Z out is equal to 0, just to keep it simple. And then I will take it from there. Okay, so P in by gamma, again, this is a vertical pipe, or so I will use Bernoulli's. U in square by 2G plus Z in is equal to P out by gamma plus U out square by 2G plus Z out plus HL. Now let's discuss U out. So U out is in pipe 3. So I'll just call this U3. Okay, U3. U out here is in pipe from pipe 1. So that will call U1 square. Okay, so depending on what my first point, so I'll use my first point as this in and out as this. So that's why I'm using in and out. And that's U1 square and U3 square. I also know U1 into pi D1 square by 4 is equal to U3 into pi D3 square by 4. Okay, so it's asking for the outlet velocity. So because that way I can now say U1 is equal to U3 into D3 square by D1 square. So I'll use this to substitute here. Okay. And by the way, this is also equal to U2 into pi D2 square by 4. And so I can use also to say U2 is equal to U3 into D3 square by D2 square. All right, hopefully that's clear. So first, I can cancel P in and P out because it has been given to me. They are the same. Then I also need to know HL. So HL is U1 square by 2G into FL1 by D1 plus U2 square by 2G into FL2 by D2. I have to add all of them. U3 square by 2G into FL3 by D3. Okay. Another thing to note here is that it's very important to note that there is no minor loss. Ignore the minor losses, so I don't have to worry about any minor loss. I just have the major losses. All right, so now we come to the substitution part. I want to substitute everything in terms of U3. So I'll come to Z in minus Z out. So Z in minus Z out is equal to U3 square by 2G minus U1 square by 2G plus U1 square by 2G into FL1 by D1 plus U2 square by 2G into FL2 by D2 plus U3 square by 2G into FL3 by D3. Now, luckily, friction factor has been given to us as constant, so we don't have to worry about it. And I can just take it out from the system. So now it's important to see, I can say U3 square by 2G minus 1 minus U1 square by U3 square. Now U1 by U3 is D3 by D1. So this is D3 D4 by D1 to the 4 because this is the square of, this is U1 square by U3 square. So D3 by D4 minus D3 by D4. Then I can also say F is common. So let's actually just say, it's will be simple to say D3 by D4, D1 to the 4 into FL1 by D1 minus D3 to the 4 by D2 to the 4, FL2 by D2 minus, and U3 is common, so this is FL3 by D3. So that's the right hand side. Now I'm still left with why do you ignore minor losses from the question? Okay, so yeah. So now Z in minus Z out. So that's the second part. So how I can go in from Z in minus Z out? So first I know this is L3. So this is L3 sine theta. Sorry, L3 cos theta rather, because it's the vertical angle. Then this is L2 sine theta. And then this is the back part here is minus, because I'm going down now, minus L1 sine theta. So I'll go up first and then down. So it's L3 cos theta plus L2 sine theta plus L2 sine theta minus L1 sine theta. So Talal, hopefully this answered the question, but I'm happy to go through the detail if any step was unclear.
Yeah, no, it's clear. But so if for example, I have 4 pipes instead of 3, and there is like minor losses and major losses. Do I multiply according to the chart that's in the end of the practice exam? There is the flanged and threaded thing. Do I multiply the number of the pipe by KL and add them together?
Yeah, so that's a good question. So we'll explicitly mention that assume that the losses are in each bend. So for instance, if you say each bend, there'll be 2 bends here, right? So we'll give you that information. Don't feel like you will have to judge that. Like in your homework, you had to kind of judge that. It will not be like that. We'll give you that information explicitly.
Okay, thank you so much.
Yeah. Any other questions on this problem?
Yeah.
Yeah, I
just
got.
like
Yes, go ahead, Hassan, first, and then we can go again. Yeah, Hassan, go ahead.
just like the L sine theta, why is it negative?
Sorry, can you repeat again?
Why is the L sine theta negative? The
Oh,
L1.
yeah. Yeah, so it's negative because I'm first going from, let's say this is 0.1 or let's say 0.3 or rather A to B here. Then A to B is positive, B to C is positive, then C to D is negative, right? So I went up until C, that's why I'm adding, and now from C to D when I'm going, I have to go negative. Does that make sense?
No, it's just because the direction it's going is that
So
all?
let's discuss this way, okay? So hopefully this will be clear. Let's say this is A, this is B, this is C, this is D. So I hope this will make sense. So what you have to find is you have to find ZD minus ZA. Okay, that's your goal. Z in minus Z out, right? Now I'm saying ZB minus ZA is equal to L3 cos theta. ZC minus ZB is equal to L2 sine theta. And then ZC minus ZD, because C is rather ZD minus ZC, because C is on top of D, I'll say it minus L1 sine theta, right? D is lower than C, so that's why it should be negative. And that's why when I add them, then I'll get ZD minus ZA. Make sense?
Yeah, that makes sense.
Okay. All right. I will go to Dylan and then sorry, Jackson and then Dylan. So Jackson, please go ahead, and then I'll go to Dylan, and then we can again iterate. So Jackson, go ahead, please.
Yes. I was wondering if we could do a problem similar kind of to problem 7, but going in the like the positive vertical direction instead of going down.
Oh, I see. Yeah. So the question is 7 going in the positive vertical direction. So let's say the turbo is in this direction, right?
Yeah.
Turbo, yeah. So this is turbo. And let's do this here. All right. So in this case, turbo, we are going upwards, and then my gravity is always downwards. And then in this case, my drag force and gravity are together. So drag force and gravity. And I'm assuming buoyancy is 0 because we are in air. But if we are in water, you may have to add, let's just add, I mean, just for the sake of it. Let's imagine you are doing like a water sport with, jumping upwards. In that case, buoyancy will be upwards. Okay. And then drag will be in this direction. So then mg plus fd is equal to fb plus f propulsion. So some value given to us. Now mg plus, and this is for terminal velocity. So I'm trying to find the maximum velocity again, because that's when the forces are balanced. So mg plus rho u square by 2 into cd times area is equal to rho times v times gravity, and mg is really rho s times v times gravity, plus fp will be some value fp given to me, and now u has to be rho vg plus fp minus rho SVG by rho by 2, rather, let's say 2 into rho times CD times A square root. Okay, so I mean, I've just skipped a couple of steps, but you can verify this and you will get this answer. Okay, and now this is a very good question, Jackson, because I hope this makes sense that my propulsion force has to be greater than my gravity force. I mean, there is some contribution from buoyancy, or in other words, for my velocity to be positive, that I am able to propel upwards, I need the propulsion force to be great, and propulsion force plus buoyancy force to be greater than the gravity force. Otherwise, I'll not be able to move upwards because gravity will keep weighing me down. So that's why I have this sum here. And because if it is negative, then I will not get any velocity. And so depending on the propulsion force, I'll find whatever is the terminal velocity. So if it's really high propulsion force, I will have a very large velocity. But if I'm just twice that of the weight, then I will just get some velocity depending on the value of the density and gravity and so on. Does that make sense?
Yes. Is the buoyant force using the density of the solid or the
Always
fluid?
of the fluid, always of the fluid. So buoyancy force here, this one is of the fluid, always of the fluid.
Okay.
Yeah.
Thank you.
Yeah, for sure. All right. Let's go to Dylan and then we'll see. Dylan, go ahead, please. Yeah.
So I have two questions. I was wondering, when you're trying to make an equation dimensionless, do you only use like that star term on the terms that are inside a differential?
Yeah, generally speaking, that's a good rule. I mean, it's like in some other scenarios which we have not discussed in the class, it's not always true. But yeah, for this course, I will say whatever is the independent and dependent variable, you have to put star on them. Yeah.
Okay, and then I was wondering if you could maybe review how to use a Moody chart.
Yeah, for sure. By the way, tomorrow you will not be asked to read the Moody chart, but you might be asked to use it in terms of so you will not, like in one of the homework problems, you have to basically go and look up the number. That is not something you will do tomorrow, but I will still go and discuss how to think about this. Okay. So let's go here. Okay. So I would say, for the sake of tomorrow's, what you want to focus on is 3 regimes, Moody's chart. So you have friction factor, you have Reynolds number, you have this, then you have the smooth pipe here, smooth pipe. These, and then the third regime you want to focus on is a very rough pipe. Okay. There is obviously everything in the middle, but let's not worry about that. Okay. So that's not something you should be worrying about. I would say this is really the crucial part. So in this part, the friction factor is 64 by RE. In this part, friction factor is 0.316 by RE to the 1/4. And for a rough pipe, friction factor is basically roughly constant. And what that number is will be given to you in the problem. And so why are these 3 regimes important? Is because for us, again, this is not true for a vertical pipe, just for a horizontal pipe. For a horizontal pipe, in this regime, which is less than 2100, in this regime, delta P will be proportional to U. Okay, so that's something you can derive from the formula. In this regime, for this pipe, delta P will be proportional to U to the 7/4. This is one of the exam problems, okay? Practice exam problems. And for this regime here, delta P will be proportional to U square. Okay, so that's what I would say focus on in the Moody's chart, and I wouldn't worry about anything particularly anything else. I'm happy to derive these as well, but you just have to plug in the formula of F into delta P by rho U square by 2 into L by D is equal to friction factor, and you will be able to get these proportionality constants. Obviously, this is assuming that the pipe is the same, length and diameter is the same. assuming that is true, you can say these relationships.
Sorry, what's the frictional factor for the smooth pipe?
So friction
It's-
factor is 64 by RE. RE less than 2100, 0.316 into RE to the 1/4 for RE greater than 4000 for a smooth pipe, and some constant number which will be given to you for RE greater than 4000 for a rough pipe. Okay, so this is, and what friction factor is? This friction factor by definition is pressure drop across this horizontal pipe, rho u square by 2 into L by D. So to read the Moody's chart, if we are given to you, you really just want to make sure you are reading it carefully and seeing that this is 1 by Reynolds number, this is constant, and this is, this dependence. But you can also keep it as in this form in your notes if that helps.
Thank you.
Yes. All right. Other questions before I go back to Jackson and Owen? Any other student has a question? Please feel free to unmute and ask. Sam, go ahead, please. Sam, do you have a question?
Oh, sorry.
Okay, no worries. All right, Owen, I think nobody else is asking the question, so please go ahead. Yes.
I have a question from Jackson's question earlier and Talal's question earlier. For upward, for terminal velocity moving up, is rho S of the, like, what is rho S?
This one. Of the solid.
Okay.
Of the
Okay.
object. Yeah.
Perfect. I was just making sure. And then for Talal's question on number 7, I understood what you said about like the minor loss. When you say that minor loss would be given, would KL be given, or would like it be like a value?
So KL will be given, and which velocity, like KL, like 0.5, 1, 0.25, something like that will be given. And it will also be told to you which velocity to use. And it will also be told to you, like, assume there is a KL for a bend, a 90-degree bend, or a bend like this. Like, it will be explicit. It won't be like, basically, my point is you don't have to feel like we will be tricking you or anything. It will be more like, oh, whenever the pipe bends, assume that there is a KL of 0.5, and assume that the velocity that dictates that minor loss is given by the entering velocity. So in this case, you will use this velocity, entering velocity. In this case, you will use this velocity, the entering velocity. So like it will be explicit like that.
Okay. And you would use like the same concepts, like where you're solving for like U3, because you get like 0.5 times, for example, like U1 plus 0.5 times U2, and then you can just use the continuity to like change U1 and U2, and then you can just pull it all out at the end.
Correct. Absolutely. Exactly.
Okay. Perfect. Thank you.
All right. Hassan has a question. Hassan, please go ahead.
Yeah. Is it okay if you scroll to the 7B question?
Yes, please.
Oh, yeah. Just I'm not sure how the FB, is there like an equation for it that you put rho VG or?
Sorry, can you repeat it again?
For FB, how did you get rho VG for it?
Well, that's the Archimedes principle. So the buoyancy force is the weight of the fluid displaced. So basically, you, instead of imagining that there is a solid of density rho s, imagine what would be the weight displaced by that solid. So it's like whatever is the volume times rho times g.
So it's like a set equation, basically.
Sorry, can you?
Is it like a set equation?
No. So it's basically, yeah, you can always assume FB is always going to be rho Vg, regardless of what it is. So this is the fluid density, the one that is outside the object. This is the volume of the object. This is always going to be true, and FB is always going to be upward. So this is what we discussed in part 1 of the course, right? That the buoyancy force is weight of the fluid displaced and it always points upwards. So you can always use this regardless of the body object shape. So like if I have a cube, you will say rho a cube g. If I have a cylinder, you will say rho pi d square by 4 times height times g, and so on. Make sense?
Yeah, that makes sense.
Okay, perfect. Other questions?
I was wondering if you could maybe go over how to like identify repeating and non-repeating variables.
Yeah, for sure. So repeating, non-repeating, repeating, non-repeating variables. All right. All right, I have to always make up some problem to think about this. Let me think of a fluids problem. Okay, so let's do this one. Let's do the turbo pack problem just for fun. So I have a turbo pack where we have a diameter D of the parachute. Okay, I'm moving with a velocity u. The like parachute and the person are moving with the velocity u. There is a drag force Fd. The density outside is rho. And just to make things a bit interesting, let's also say that there is an area A of the person, just to make it interesting. Okay. So now we have 5 variables. So our variables are rho, Fd, U, D, and A. Okay. This is ml minus 3. This is kg meter per second square. So mlt minus 2. Velocity is lt minus 1. Diameter is L. And this is L square. Okay. Now I have to choose is there a question, Jackson?
Yes, I do have a question kind of regarding this. If one of them's a function of the other ones, how
Yes.
would you go about that? Would it be the same thing?
Correct. Yeah, it would be the same thing. So I was, yeah. So basically I cannot use diameter and area together. I'll mention that. Yeah.
Okay, thank you.
Yeah. So and this is just to kind of, you will likely not have a problem like this tomorrow, but I just wanted to drive on the point. So I want to now first there are 3 dimensions. So K is 3, sorry, K is 5 and R is 3. The number of dimensions are 3. So I should expect K minus R is equal to 2 variables. Okay. So I first have to three repeating variables. Now my goal is that I should get 3 variables of distinct dimensions. So I should not try L and L square because they're practically the same dimensions. I should cover all mass, length, and time. So to cover all mass, length, and time, let's say I pick this for whatever reason I pick, let's pick density, or you can also pick MLT minus 2. I'm just trying to keep it simple. I'll say rho UD. Okay. And I'll pick these as variables. Other options, so option 1 is rho UD. Option 2 could be, let's say, FD, U, and D. Okay, you can also say option 3, rho U, A. That's also fine. So you can use this or FD, Okay, all of these are FDUA. That is also fine. But we can use this one. And sorry, in that case, pi 1 will be rho to the A1, U to the B1, D to the C1 times FD, and pi 2 is equal to rho to the A2, U to the B2, D to the C2 times area. Okay. Go ahead, Jackson, if you have a question.
Oh, sorry, I forgot to lower my hand.
Okay, no worries. Okay. Yeah, so if you will do this, and I'm just in the interest of time, I will just write the answer. You will get rho U square D square for pi 1, and pi 2 you will get A by D square. Okay, this is what you will get as pi 2. So try this out. This is what you will get is a pi1 and pi2. Now let's go with this option. So in this option, I will say pi1 is rho to the a1, sorry, fd to the a1, u to the a2, d to the, sorry, b2 and c2, sorry, b1 and c1, u to the b1, d to the c1 times rho, and pi2 is fd to the a2, u to the b2, t to the c2 times area. Okay. And now if you will do pi1 c1 here, you will get pi1 is equal to rho u square d square by fd, and you will get pi2 to be a by d square. So you can see these are very identical, but this is just the opposite, inverse of this one. So that's fine. And they are the same. Finally, and again, this is very good practice for you to do. If you will do this one, I will just give you the answer. You will get pi1 as fd rho u square a. Okay, and then pi2 to be d square by a. Or rather, sorry, d by square root of a, apologies, d by square root of a. So you can see they are related to each other, but they are different in different choices. What you cannot do, option 4, for instance, what you shouldn't take is you don't take a rho. Actually, that's not, but don't take, let's say, fd, a and d. This is not allowed. Please don't take these ones because a and d are not distinct in dimensions. They basically are the same dimension, just squared. So you will not be able to close out your system of equations. So just make sure that the three variables you're taking have a different type of dimension. Like one is length and time, one is length, one is ml minus 3 and stuff like that. Okay. So, and you can try this. You can try this yourself quickly and you will find that this doesn't work. So don't use that, but rest everything should be fine.
What are the dimensions of FD?
Is the Newton, it's the force. So Newton or kg meter per second square. So mlt minus 2. Does it answer a question about repeating, non-repeating? Any questions here? I'm happy to discuss more.
I was
Mhm.
wondering if, like, because I know you're not giving us the dimensions of these. I was wondering if we need anything more than like diameter, density, velocity, viscosity, length, pressure, and like the drag force. Is that all we need?
No, I would say pressure, tau, shear stress, torque, frequency, I mean, and I may be forgetting some variables, but, what is the kind, rotational speed omega, u, surface tension, specific weight, gamma, shear rate, gamma dot. What else comes to mind? Viscosity mu. I've forgotten viscosity mu. What else does it occur? Force, torque, pressure, density. Yeah, I can't think of other variables right now, but these are the ones that come to mind right away. But yeah, you will have to be a little gravity, gravity, acceleration, time, and stuff like that. I mean, just the usual one. I believe might be a dimension. I mean, I don't remember the table number, but if you're not good with remembering some of these numbers, there might be a table in the. Let me even check. We might have even uploaded it in the course file. I'm pretty sure we did upload it. Yeah, it has table 1.1 common dimensions. I would just, write down all whatever is there. That's all you will need ever. I don't think you will need anything more than that. So there is one on the one page dimension list in the on the course page.
Thank you.
Any other questions, anyone? Let me check chat. Okay, I think we addressed the negative part. Any questions?
Yeah, can we do something similar to problem 2, but in a different setting?
Yeah, go ahead. What kind of setting do you think? Do you have a suggestion in what kind of setting you're thinking? Problem, is it practice problem 2, right? Practice exam problem 2?
Yeah.
So like, yeah, what we can do, like maybe that's a good one to think about, is what to do if it's a turbulent pipe. So that's a good one. So maybe that's something we can think about. What is, and let's do this. Actually, let's try to make things interesting. So the question could be, you've been given a vertical pipe. Okay, you're applying P in, P out. Okay, and the question is asking, so I think we discussed this line that there is some gravity. This is non-zero because it has to also push against gravity, the P in versus U. But the question could be something like, what are the conditions, right? So as we have discussed, it is proportional to U. So P in, like P in is equal to Z out by gamma was Z out by Z minus Z in plus U square by 2G into FL by D. So if F is constant, which is a very rough pipe, you will get the maximum increase because it will be square of velocity. If this is a smooth pipe, you will get U to the 7 by 4. Okay, so it will be this one. It will be gentler than rough, but still quite like this. And it is linear because it's laminar. So the friction factor condition can change. That's one option, I would say. You can make things more complex, but I wouldn't know how to. It will be a little bit harder for me to guess, essentially. One thing you could try is think of like a network of pipes, but I wouldn't be able to directly. I have to think a little bit more about the question. In this case, it's like this. So now P in by gamma and now my V in and V out and V in are not the same. So you will also have Z out minus Z in, U1, U2, L2, L1, D2, D1. Then you will have Z out minus Z in plus U2 square minus U1 square by 2G because they don't cancel, U2 and U1. And then U1 square by 2G, F1 L1 by D1 plus U2 square by 2G, F2 L2 by D2. And of course, I'm not assuming any minor losses are zero. So this can be another option where basically this is kind of like the longer problem we did. But as you can see now, we have to use flow rates to make it in terms of one velocity and so on. So that might help. And this is Z out minus Z in is L1 plus L2 because this is Z equal to 0. This is L1 plus L2. So yeah, that is another question you can think about, but hard to think of another variation or twist of something similar. Other questions, anyone? Happy to answer any questions. We also have another office hour, obviously, in a few minutes. So you're also welcome to go and attend that one.
Thank you, Professor.
Of course, pleasure.
Thank you.
Of course, my pleasure. Of course.
I have a question more general, I guess. If like we finish, sorry, if I understand the practice material, and I think I do understand, do you think that'll be enough, or should I go over like the homeworks and the additional practice problems?
I would recommend, if you have the time, to go over, just because, I mean, this exam is representative, but I would recommend, if you have the time, to just go through more material just to get more practice, because, more practice is just going to make it easier for you. So it's always the case, I would say.
All right, sounds good. Thank you.
Yeah, for sure.